Okay, students, just a reminder, I got a bunch of text messages last week and actually since the beginning of the semester. Dr. B, when are your office hours? And actually, it's on this slide every day. It goes right by it. It's as plain as the face on your nose. I mean,
Exactly.
as plain as the nose on your face. Anyway, yeah, so we'll have office hours tomorrow. Oh, by the way, I want you to look at your printout. As always, you should do this every time you get it. And see if you have any double answers or if you have any blanks. And if you do, drop it off with me before you leave, if we have time, or come to office hours tomorrow and we'll double check your Scantron. Now, every time there's a few people that, they didn't bubble in one of the dots dark enough, or they forgot it, that'll be a blank, or they didn't erase well and it looked like 2 dots, but I'll be able to figure it out. The computer, Lindsay, can't necessarily figure that out, but I can figure that out, right? So bring those to me when we dismiss, hopefully a little early today. Would you guys like to dismiss early today? Maybe? No? Somebody over here said no. Oh, now. No, we can't dismiss now. That would be too easy. All right, comments about the exam. A couple students asked me what the average is. And I don't have the printout with the average on there. But for the other class, it was about 72 on the Scantron. So a little bit higher. And by the way, when I hand back your exams, sometimes I say good job. Or sometimes I drop it. It's too hot to handle because it's a really high score. If you get on a 40, this is 41 points. So I was students that were getting 31s or more, I was saying good job. Because that means you got like about a 75%, something like that, on the Scantron part. And that's a B. So that's pretty good. And if you got above 35, that means you got pretty close to an A on the Scantron part. So that's good, right? And anyways, the average. Now, the reason I don't have a true average, an accurate one, is because we got all these people at the bottom of the stack here with PIDs all blooped up. So we don't have their scores, but we're going to get their scores and hopefully have an accurate average on Thursday. I usually do that during my office hours on Wednesday. So, okay, we just handed out your Scantron printouts. As always, keep those. And the blurb sheets, I know I still owe you blurb sheets from exam 1, but exam 2, everything's copacetic, COPACETIC. And everything's copacetic for these exam blurbs, and so I'll be posting them after class. First I'll do the YouTubes, and then I'll post the blurb sheets. So maybe by supper time tonight you'll see them. All right. You'll have, on this one, things are going to be a little different. When you look at your grades page, you may have already looked at it today. You'll see 3 different subscores. Now, the exam 2 Scantron, that's the one that you have in your hand. Okay, that's the portion of points that come out of the 41 dots on the Scantron form. Okay? So you have somewhere between 0 and 41 in that row of the grades page. Now, Caitlin, there's another row below that. It says exam 2 clicking. That's 9 points. That's the first 3 problems. We had 2 Tweety Bird related problems and then 1 boxcar problem. And I saw an awful lot of people clean house on everything, and they got all 9 points, which means I have to start writing tougher tests, right? No? Or you guys have to just keep studying hard, which is good. That's what I want. Anyway, I saw a lot of 9s. Anyways, so that's the part that says exam 2 clicking. Now, I'm separating out the very last part, the 4th question. That was the bonus question, the code question, and that'll have its own line. And I haven't finished grade. In fact, I haven't even started grading those. I've just kind of separated them out from the others. But I will grade them in the next 48 hours probably and post those as well. So right now, what you can see are the score from clicking, 0 to 9 points, somewhere in there. And after class, I will unmute the Scantron score, but you've already got it, so it's not a big mystery. But I always mute those scores before I hand out Scantrons, because I like you guys to have the Scantrons and see it here first. So that's what I like to do. And then the codes will, hopefully this week, we'll get them scored and analyzed and everything like that. Because I have a feeling there's going to be a lot of interesting answers, and I'm very, very interested in how you answer those. So I look at them all individually and give a score. 0, 1, 2, or 3 points. Now, also, I would like to remind you that we will keep the best 2 out of 3 midterms, but only if you are here for all 3 midterms. And that's most of you have been here for all the first 2. So that's good. If you can make it to exam 3 and hopefully bring your grade up a little bit higher than even this one, then we'll drop your low grade. But if you miss exam 3, then you're stuck with exam 1 and 2. There's nothing I can do about it. All right? So try your hardest to get here for exam 3, and of course study and get ready for it and be here, and then you can have the luxury of dropping your lowest grade. And that'll automatically bring your average up. So, and as always, keep clicking in class. Keep doing your homework. That goes without saying. You know, I saw something really interesting. I computed midterm grades for my online section. And their grades are a little bit different from yours. They don't have clicking. So they have homework and exams. And there were a few students that have Fs. But the students that have Fs missed a midterm. Most of them missed exam 2 for whatever reason. Now they have best 2 out of 3, so if they're here for exam 3, their grades will probably be up in passing. But it's something that I've mentioned to you before. If you want to get an F, the easiest way to do that is to miss class and especially miss an exam. All right? But if you want to stay in the sunny side of the street, grades-wise, then make sure you're here every day. You click every day. You do your homework faithfully, and you take every exam that's possible. Okay. Now, somebody had a question. Joseph.
Yeah.
Right.
Is the bonus part of the exam, like say exam 2 got dropped, do we still get to keep that bonus as like a general grade thing, or does it?
What do you think? Should I still let Joseph keep his, if he drops exam 2, should we let him keep his bonus? Yeah, I always do that. Yeah. Yeah, those bonus points don't go away. So those are like, if you earn them, baby, because that's usually the hardest stuff, the bonus points. Okay, so if you earn them, you get them. You keep them. Caitlin. SSG study groups. The question was how many points for the SSG study groups? The answer to that is 4 points for each SSG that you can attend, and that you sign the attendance sheet, and then the SSG leader gives an attendance sheet back to me, and then you get the points. So we won't have enough SSG groups for everybody to attend, but we should have enough for a bunch of you to attend. Okay, and usually what I do is I give the first dibs at joining up to the special study groups for those students who have the lowest exam score, the lowest exam average. But usually there'll be some spots after I open it up for anybody. And so usually there's a good number of spots left. So, but that we'll start forming those in the next week after I get all the exams done and figure out everybody's average, and then look for people that have a 90% average on the first two midterms, and then I have to send out invitations. Who's going to be an SSG leader, and then they have to accept. They don't have to. Well, they accept, or if they don't want to participate, they don't have to. And then we form the groups, but by exam 3, we'll have that running. Okay, and you'll get if you sign up for an SSG group, and then you attend, and you sign the attendance sheet, and the SSG leader gives the attendance sheet to me, then you'll have 4 points. Okay, and those don't go away, even if exam 3 gets dropped for you. Okay, just kind of like what Joseph was saying. So if you get a bonus, even if we drop that exam, you still have a bonus. Right? I think that's fair. That's pretty easy to do. Another question. Okay, last reminder is that midterm 3 is a Tuesday, the 24th of November, so roughly a month from now. All right, so we've got a lot of stuff to cover, and then after Thanksgiving, we'll have, I think, one more lecture, and then we'll have the final exam week right after Thanksgiving usually. So we don't have much time, but we're gonna keep going and work our you-know-what off, and hopefully things will try to avoid spiders over there, and learn a lot. And what I want to learn a lot today is about averages. And you may think, oh, Dr. B, come on, this is like 6th grade math class. Yeah, right now it is. But we're going to be doing some concepts based on averages that is definitely not 6th grade math class technology. So get your clicker out and get your calculator out. Get your brain on. Sarah, you ready? Your brain is ready? Okay, good. Just checking. I'm not saying nothing. I'm just checking. And let's do a simple question first. Simple, simple, simple. Here it is, multiple choice. What is the average speed? And as always, we're on frequency BB. Colin, I got your clicker. Colin, where are you at? You're good on clickers now. Did you see my message in web courses? Yeah. Take a look. I texted you this morning in web courses. All right, compute an average. And if you can't remember how to average something, ask your neighbor. $30 seconds. Boy, I wish I could remember more of your guys' names. It's difficult. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys got cooked up here. Yeah, this is average 15.03 is correct. Most of you got that. A few of you, for some reason, a few of you voted for 14.43, and I made that up to be tempting. It looks like about 11 of you voted for it, but you know what? I can't remember exactly how I cooked that up. I think that might be, I don't know what that is, 14.43. 60.12, you know what that is? Only 2 people voted for that. That's just the sum of these things. But then, you know, for an average, you add them up and then you divide by how many. So if you don't do that, you're SOL. And 15.03 is the answer for that, which most of you guys got. So that's good. Okay, now that's a simple one. Let's try another one. Hit the refresh key, and you're going to actually type in a number now. So this is going to be another calculation, a little bit tougher. And it's a table of x's and y's. And just calculate, again, the average y value from this table. And do it carefully. And as you do, you know, this one you might want to jot down in your notebook, the table of x's and y's. And as you work on that, it might be good to look for patterns. You see anything interesting in that table of data? And a student brought something up that I hadn't noticed, which was kind of cool, actually. Are you cold? These rooms, sometimes they're hot, sometimes they're cold. You know what's really bad is the mathematical sciences building, that big lecture hall in the basement. Oh, man. Always cold down there. 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh, man. You guys are geniuses. 97% of you got it. Look at this, though. Look carefully. The one person voted 195. What does that tell you? They messed up the decimal point. And hey, you guys, I apologize for that decimal point. It is really tiny and very hard to see. So if this were a test, I would say to that guy, okay, I'll give him partial credit. Or maybe even full credit. Because, you know, missing that decimal point, it is not hard to do. And so, but most of you got it right. That's good. Now, you may be thinking to yourself, Dr. B, these averages are nice. There's something interesting to see. But did you see anything interesting in this table of data? Did you notice any patterns or any kind of cool. What do you see, Dante? Yeah, you're looking at the differences in the delta y, right? Yeah, look at delta y. It goes up by 7, up by 5, up by 3, up by 1. Those are all odd numbers to 28. And then it goes down by 1, down by 2, no, down by 3, then down by 5, down by 7, and then down by 9. So it fits that pattern. So that's kind of interesting. And that is significant. It's a significant pattern. So the delta y's are increasing. Anything else did you notice? What else do you see? Or how else can you say something interesting about this set of numbers? What do you see? It gets, I could barely hear you. Oh, okay. So it starts low at 1 and 10, and then it gets, and then the top value is at 5. Yeah, okay. So it's kind of, it's going up and then it's coming down. Sarah Rudolph. One and 9 are the same, 2 and 8. So 3 and 7. 4 and 6. And then 5's right in the middle by itself. What do you call that? What do you call it? Come on, in the green t-shirt. You're saying something. Yeah, you. Huh? Nope, it's not inverse. What do you call it? A parabola? Oh, you mean like this? Yeah. It's symmetric. It's a parabola, a parabola. And I programmed it in like that. I knew that I wanted to give you guys a parabola, so I made the table true parabola data. And so go ahead and sketch that. Does that make sense, Sarah? I mean, everybody's described the same thing. I mean, because if you think about it, Dante, you know, between the first delta y between the first two is big. The next delta y is a little bit smaller, a little bit smaller, a little bit smaller yet, and then it starts going downhill, and it's all symmetric. So we've got a left-right symmetry in this. Go ahead and make a note of that. There's a left-right symmetry in this data. It does map out exactly to a parabola. I ran my parabola out a little bit to x equals 10. So the graph is not symmetric, but the function is symmetric. The vertical line right through 5. The dashed line is the average value. Okay, 19.5. And you can see that it's, you can't really see it too well on this screen, but it's just a little bit below 20 at 19.5. All right, so now here's the cool thing. If you compute the area of that rectangle between the dashed line and the x-axis as a rectangle, it will be fairly close to the area underneath the parabola, from the parabola down to the x-axis. It won't be exact, but it'll be close. And if we had made measurements every half meter, then we would have an even more accurate average. Now, you might be saying to yourself, Dr. B, what is this sixth grade average business? Okay, parabolas are very nice. Patterns, okay, I see it. It turns out that to study gases and molecules in general, temperature, pressure, all that stuff, all the properties that gases have. Liquids have temperature as well. Liquids can have a pressure. Solids can have a temperature. And they're all made of molecules or maybe atoms. You know, like carbon is a diamond is a crystal of pure carbon. So if you have a diamond ring or a diamond earring, diamond anything, that's a bunch of carbon atoms. And what we're going to do today is take a look at the foothills of this big mountain range, the gases and temperature and molecules mountain range. And the first part of that is the kinetic theory of gases. So, but for molecules in general, we have this vision or this kind of hypothesis, Darian, about what molecules are. Now, we're going to consider first this kind of idealized view of what gases are. And then we'll bridge out to liquids and solids after that. So first, this kind of idealized concept of a gas being a collection of molecules, you know, the ancient Greeks thought of atoms. They didn't really think of molecules, but they did think of that everything was made of atoms. At least some of the Greeks did. And then around the 1700s, people got more serious about that idea, and they started developing the molecular theory. And in that, as a subset, is the kinetic theory of gases. And assumption number one is that there's a huge number of them. They're really teeny. You can't see them. And that they're really far apart. So now, when I say a huge number, here's what I'm talking about. If you go down to the grocery store and you buy one of those little helium balloons that says "Have a nice day" on it or "Happy Birthday" or something like that, or any other balloon like that, it's going to have a bunch of helium gas in there. Okay, the number of atoms of helium in that balloon is going to be something like 10 to the 23rd power. Okay, so so it might be 1.5 times 10 to the 23rd power. So write down a 10 and then an exponent 23, and that is the order of size of how many molecules in an everyday sample of a gas. Okay, now if you have a big scuba tank, you might have a lot more than that. You might have 10 to the 24th power. But if you have a little teeny sample of gas, or if you're looking at bubbles in glass, when a glass cools, sometimes it has little bubbles that are captured and still, they haven't, dissolved out or anything like that. So that would be a little, so you might not have 10 to the 23, you might have 10 to the 19 or something like that. But it's still a pretty big number. And we've actually found meteorites from Mars that have landed on Earth, that we analyzed the little teeny bubbles of gas in the rock itself, because when it was blasted off the surface of Mars, it melted a little bit and captured some of the atmosphere of Mars. And it was blown off into the space at the same time, so it melted quickly, then cooled quickly, captured the gas, and as it did that, it flew out into space and eventually landed on Earth. And somebody down in Antarctica picked it up, and they analyzed those little teeny bubbles of gas, and they figured out, yeah, that's the same as, all the atmosphere measured by all the Martian spacecraft that we've landed on the surface. So we know what the Martian atmosphere is like from those landers. And when we analyzed that little teeny bubbles of gas, we figured out, yeah, that's from Mars. It's kind of cool. A rock from Mars. And one of those meteorites from Mars, they think, has a sign of life in it. Very small, molecular-sized organism. Kind of cool. But it's also kind of controversial. Some people say, nah, it's not really that. So we got this molecular gas, kinetic theory of gases. Huge in number, very teeny, can't see them, but they're also really far apart from each other. Second assumption, in addition to being a lot of teeny little particles and zillions of them, second assumption is they have a whole distribution of speeds. It's just, chaotic, random distribution. So a lot of small speeds, a lot of high speeds, a lot of medium speeds, and all different directions, and just, chaotic, a gas. Third assumption is that they ricochet around off each other and off the walls of the container, whatever container it is, like the walls of a scuba tank, the sides of the balloon. But otherwise, they don't interact. So they don't have a gravitational interaction, right? And they don't have an electromagnetic interaction, a long-range electromagnetic. So in other words, like a magnet, if you have a good, strong magnet, you can pull paper clips to the magnet from quite a ways away. And some of the magnetic, they had an accident up at University of Florida here over the weekend, I think. A guy got killed. They have really big, huge magnets up there. And apparently something went wrong and a guy got killed. Maybe something fell on him or something. But those magnets that they got up there, and even here next door in the Physical Sciences building, I'm sure they have some really strong magnets. So if you drop like a pen or like a paper clip, you might kind of knock it off the side of your desk. And if it skitters across the floor towards that magnet, it'll then get sucked up right into the magnet against gravity. They're so strong. They're really strong. When they're turned on, they're electromagnets. So this assumption in the kinetic theory of gases is we don't have anything like that going. We just have little BBs ricocheting off each other or ricocheting off, bouncing off the walls. Other than that, no interaction. And the fourth assumption is that whatever happens, they obey Sir Isaac Newton's 4 laws of motion, i.e. F equals ma. And go ahead and put down the word there, etc. F equals ma, etc. Okay, so in other words, they obey the first law and the third law also. Momentum. Now, go ahead and add one side note here. So this would be 1E, 1 echo. So my side note is, because they're so tiny, so far apart, so unseeable, so difficult to see, we cannot know the dynamical state of individual molecules. Let me repeat that so you can copy it down carefully. Because the molecules are so small, because there are so many of them, we cannot know the individual state of position and momentum for any single molecule. However, we can figure out average momentum, average kinetic energy, average position. That we can handle. And that is why we had 2 clicker questions to start class today concerning averages. And let's talk about that now. The kinetic energies, we cannot know the kinetic energy value for any given for any given molecule. It's impossible. There's too many of them. They're too teeny. They're too fast. Just the last 10 years or so, we've been able to see a few molecules, some molecular rings, carbon rings, like benzene and stuff like that. We've been able to see that, but it's not easy, and it's only the last 10 years or so that we've been able to do that. But like back in the days of Sir Isaac Newton, they weren't even thinking about molecules. And then in the days of Michael Faraday and Dalton and all those guys, like in the 1800s, the early 1800s and on up, they were thinking about molecules, but they could never see them. That's why they had to make these assumptions, the first 4 assumptions. But they worked out all the math, and they figured out a fairly good theory, the kinetic theory of gases, and it actually it leads to lab experiments where you can predict an outcome, you do the experiment, and find out if your prediction is on the money or not. And their theory is pretty good. They can get things on the money. Now, the kinetic energy of the molecules, we can't know them individually, but we can know this basic idea that there's a huge range. So there's a lot of kinetic energy for some of them. There's really pokey kinetic energy for some of the others. And then there's everything in between. So there's a big range of kinetic energies possible because there's a big range of velocities. Speeds are distributed randomly. And sorry, this is supposed to be 2A and B. It came out 2E and F. You can modify your notes to reflect that. Second comment here, the average kinetic energy is proportional to the absolute temperature. So this one, your side note to this little item, the second item there about average kinetic energy, if you apply 2 big mathematical tools, statistics and calculus, and actually a little bit of trig to go with your calculus, you can get this basic result. That the average, if there's zillions of these things and they're obeying Newton's laws, I might not be able to get individual kinetic energies, but I can get an average if I use calculus carefully. And it turns out that that's proportional to the actual temperature in the absolute scale. So in other words, if you measure the temperature, just multiply it by a certain number, and that's the average kinetic energy of a molecule. Now it's an average, it's not the actual, but there's going to be a lot of molecules with that average energy. Now, underline the phrase absolute temperature. What is the absolute temperature? Well, if you remember your Fahrenheit scale, that's based on water. The freezing point of water, 32 degrees Fahrenheit. The boiling point of water, 212 degrees Fahrenheit. Celsius is the same. 0 Celsius is the freezing point of water. 100 Celsius is the boiling point of water. All right, so that's normal. Those 2 temperature scales are oriented to the behavior of water, but they are not absolute. The absolute scale is based on this idea of kinetic energy. If you have temperature, you have kinetic energy. So if it's so cold it doesn't have any kinetic energy, it keeps getting smaller kinetic energy, smaller average, smaller average, smaller average, smaller average. What happens if the average is 0? Okay? Well, that's the 0 point of the Kelvin scale. And this was adopted or invented by a fellow named Lord Kelvin, that was his British, he was a British lord. And his real name was William Thomson from Scotland. And he was so famous and such a productive scientist that the Queen Victoria made him a lord, Lord Kelvin. And he adopted this scale over here, the Kelvin scale. So this one's the 0 point down here for the Kelvin scale is theoretically the place where there's no random motions. The kinetic energy average is 0 down here. Now they postulated that theoretically, and they figured out that it has to be at minus 273 Kelvin. Excuse me, minus 273 Celsius, and 459.67 Fahrenheit. Now we're not going to do jack with the Fahrenheit scale, and we're going to do very little with Celsius beyond this diagram. All the stuff that we're going to do, thermodynamics, temperature, and all that, is going to be on this Kelvin scale. All right? And so this whole idea of average kinetic energy, classically speaking, without thinking about quantum mechanics or anything like that, you can think of it as the place where the average energy is 0. And so Lord Kelvin said, let's make our thermometers, let's make that the anchor point. You guys feel like dismissing early? All right, so let me give you a homework assignment. Read up to section 5.4 and including section 5.4 in the e-text. And check for my notes. I've already started setting, and I'll be setting more highlighter notes in the textbook between now and Thursday. You're dismissed. Come up here if you want to get your printout and you didn't get it already, or if you have any other questions.